Okay, good evening, everybody. Welcome to Papa Lim Physics Classroom. Okay, today we'll be running through the assessment or the quiz that I given for my express classes, the physics class. The topic will be on forces, then your mass weight density, and followed by moments. Okay, these three topics. Okay. If you're still confused about like whether you are doing physics or you're doing combined science, okay, you look at the video in the first on my playlist. Okay, the first video I will actually talk about in details about the differences between combined science and pure science. Okay, so you can take a look if you're not sure where you are, okay, or whether your child, okay, if you are parents, whether your child is taking combined science or pure science. Okay, now without delaying, okay, we will look at the paper itself. Okay, let me take a look. Okay, this is the assessment, the WA2 paper that I given to my students. Okay, if you have the paper, okay, or if you want to try out the paper, okay, the paper I left it in the in my Google Drive. The link to the Google Drive is in my description below. Okay, feel free to go access it and download the paper to try. Okay, remember, complete your revisions. Okay, then after that you start to try the paper. Okay, not before. Okay, so if you need a paper, it's in my Google Classroom, and again the link is at the description section. Okay, now if you have already done it, okay, here is the MCQ question. You might want to pause this video and actually copy down answer or double check your answer first. Okay, if you have done that, okay, then we'll look at each of the question in detail. Now, question one is I would say a standard example that we are looking at for Newton's law question. Okay, for whether it's first law or second law, commonly what we are looking at is that we are given an object which is under, based on the question, is under the influence of, let's say, a particular force. Okay, so there is a force here. Okay, so what happened now is that there is no friction. Okay, based on the question, there is a frictionless surface, so there's no friction, no opposing force. So at this particular instance now, the object is actually, there's only a force acting on the object. So the object net force will be, at this instant, the net force, okay, will be MA. Okay, the only force they are looking at is only force equal to MA. Okay, at this situation. So definitely, if you look at the equations on my left side, okay, it's a positive number F, okay, which means it also will tell us that the object will actually experience a acceleration, okay, because the left side is positive. You look at it in mathematics, okay, the left side will be positive, meaning the acceleration will definitely be a positive. But now what happens is the question says that when an opposing force of the same magnitude act on the object now, so opposing force of the same magnitude, so let's say I call this F1. Okay, same magnitude, same magnitude. The only difference is in the opposite direction. So if you look at it in the Newton's law, okay, you look at the sum of forces. I now actually have two forces acting on it and in both opposite direction. So the sum of forces will be big F minus F1. Okay, and true enough, okay, you will find that if both of the forces F and F1 are of the same magnitude, I will actually have my left hand side to become a big fat zero. Okay, because the two forces are the same. So if the difference between the two forces will definitely be a zero, it will imply that my acceleration, okay, MA equal to zero, and this will imply that my acceleration is actually zero. Okay, because the mass of the object cannot be zero. So it will only tell me the object is traveling at acceleration equal to 0 meter per second squared. Now remember, for Newton's first law, when you have A equal to 0, there is always two particle situation. Okay, remember, the object, it can be stationary, or it can actually continue to move at the same velocity, what we call a constant motion. And the only way to distinguish these two sections or these two motion is to actually observe what was the previous motion. For example, if the object was actually traveling at constant velocity, at a certain velocity, okay, it already was traveling. So when you have a force F1 applied to it, when the net force is 0 on the body, he will actually continue with his last velocity. That's what we mean by he will continue with a constant velocity. And similarly, if the object was actually already stationary, it was already not moving, okay, upon experiencing this net force F and F1, okay, you'll find that the net force is 0. The object will still remain as its last position or last motion, which is stationary. Okay, so it depends on your previous motion. Okay, so for this object here, based on the first case here, based on the information, originally he was already moving. So there is definitely a speed there. So which means upon experiencing net force 0, he will constant move with a constant velocity, or he will move at a velocity that is last experienced. So that's what I mean by he will actually move at a constant velocity. Okay, he will not slow down yet. Okay, he will not slow down yet. Okay, because the forces is still the same, the magnitude is the same. F1 is the same magnitude as F. So the resultant force does not allow him to decelerate yet. Okay, so students, you have to take note of what is the situation that we are looking at. Okay, for question 2, sorry. Now, question 2 is a good example in the sense that there are different variation of this type of question. For example, right, the question will say, oh, the object is falling at terminal velocity. Okay, falling at terminal velocity, it means one information. It means the net force experienced by the object is actually equal to 0. It's definitely 1. Because for net force, terminal velocity means the object has to be traveling at 0 acceleration, which means the speed has to be a maximum number and it's a constant number. Okay, or what we call a constant number. Okay, and this number happens to be, as a name for it, it's called terminal velocity. And one of the important things that we know, okay, when we have net force equal to 0, it means that the forces experienced by the object is actually equal to 0. And in this question here, there is 2 forces. Okay, in free fall, there's 2 forces experienced by the object, which is the weight and the acceleration. And the moment you know that there's these 2 forces and the net force is 0, okay, same as question 1, it will mean that these 2 forces has to be equal. Okay, and the only thing that differentiates them is the motion. Is in the direction. One is pointing downwards, one is pointing upwards. So I will know that, okay, they have to be of the opposite direction and they have to be of the same magnitude. That's why the answer is D. Okay, and likewise, net force is 0. Definitely this will fit the answer. Now, other variation we are looking at is the question can be given. Okay, so other variation that we are looking at is other than terminal velocity. The question can be asking for the object is moving at, okay, describe the motion of object at maximum height. Okay, or what we call highest maximum height. Okay, or when you throw the example, you throw the ball, okay, up in the air, and what happened? Describe the motion or describe the forces at the highest location. When the object is going at maximum height, there are a few things that you must take note. At maximum height, some of the specification that you need to know, for example, at maximum height, okay, of course, like what the question mentioned, at maximum height, it means that the height above ground is actually the maximum. That's the first criteria, or that's the first clue that I can get. Second thing is I can get is at maximum height, okay, at the highest location, the object is actually momentarily at rest. Okay, at the highest point before he start dropping down. The moment he go all the way up, okay, before he come down, that point, that split instance, okay, the velocity is actually 0 meter per second. Then last one that you have to take note is one of the specifications for highest point. Okay, when we talk about free fall at highest point, although the object is 0, and the velocity is 0, but it doesn't mean the acceleration is 0, because at that point he's actually falling under the influence of gravity. So gravitational field strength 10, okay, is still affecting the object. So which means the acceleration at that experienced by the object at that point is what we call your gravitational field strength, or what we call your free fall acceleration due to free fall, which is 10 meter per second square. Okay, so when you're looking at an object being thrown up, okay, at the highest point, okay, there are certain clues that you need to take note, certain specifications that you need to be aware of, okay, such as if the height is maximum, the velocity will be 0, and the acceleration will be 10 meters per second square. Okay, similarly to terminal velocity, there are certain specifications, there are certain criteria. Okay, when we mention terminal velocity, which actually remains the same for a terminal velocity motion. Okay, and likewise, there are other motion, like maybe the object at its lowest position. Okay, there are certain specifications. We will talk about it in detail when we come to chapter 6. Or if you actually want to know about it in detail, it's actually in my chapter 6 video. Okay, you can click on the playlist and you can look at energy, okay, which is chapter 6. Okay. Now for number 3, okay, number 3 is quite straightforward. Most of my students have nothing wrong. The important thing to highlight is actually mass remain constant. Why? Okay, because mass is the amount of matter in the object. Okay, if whether it's Earth or Moon or other places, as long as the object doesn't change and doesn't get chipped off or doesn't get dropped or doesn't get reduced in size, all these things, the mass always remain the same. Question four, not a big deal. Is a classic example. The common thing I would say, the most common mistake I see, not a lot of students make this, is the formula. Where the formula is density equal to mass over volume. Okay, so remember to use the right formula. Not mass times volume, it's mass divided by volume. So if I'm looking for density of the plastic material, I have to have the mass of the plastic. I definitely have to have the volume of the plastic. Volume of plastic straight away, okay, straightforward, 85 to 103. Okay, so 85 to 103, okay, you will definitely have the volume, the volume of the plastic material, okay, which is here. Okay, if you take the difference between 103 and 85, I will definitely have the volume of the plastic, which is 103 minus 85. Okay, if you look at your calculator, it will be 103 minus 85. It will be a number, it will be 18 cm cube. This I will have the volume, and the mass is given here, 4.5 gram. So together with these two numbers, you should be able to get the density. Okay, or what we call, okay, quite easily done. Okay. Density, number 8, not a big deal. Okay, number 6, also the same thing, so I will not go into detail. If you need, okay, number 5 and number 6, okay, just drop me a message in the comment bar or drop me an email. Okay, then I'll just send you a snippet of the explanations. Okay, if not, actually most of my students has no problem. They did quite well for question 5 and question 6. Now for question 7, okay. Question 7 is I would say the classic example of moments equal to moment formula force times distance. I always tell students this distance refer to perpendicular distance. And for perpendicular distance, there is actually a few conditions. For example, the perpendicular distance has to be between the pivot and the force that you're interested in. Second criteria we are looking at is the distance that you want is always perpendicular to the force that is of your concern. Okay, this is the two conditions. Okay, for locating perpendicular distance, normally what I tell students is there are certain techniques to look at it. The technique I have actually illustrated in my moments video, okay, which is under, if I know, moments under chapter 5. Okay, if I know it's under 5.2 or 5.1. Okay, if you're not sure about that method, okay, refer to the video in chapter 5 in my playlist. Okay, so it will be, I actually go through quite detail in that section. Okay, so just refer to it if you need to. Now for this case here, I'm looking at force F. Okay, force F, where is force F? Okay, force F, let's say, let me give it a color. Okay, let's say I give it here. Force F is here. Okay, in this direction. So how do I find the perpendicular distance? Definitely the easiest one is I'll actually copy and paste. So I'll copy and paste this particular distance. Okay, I'll copy and paste my F. After that, I will actually duplicate this line, paste it at my pivot. Okay, so the technique I always use to locate perpendicular distance is actually, I will actually copy the line, the force line. I'll copy exactly the same orientation. I will paste it at the pivot. Okay, so these two lines is what we call parallel lines, these two red color line or blue color line. So how do I find the perpendicular distance? Okay, I'll find the shortest distance between them, or I'll just simply put a ruler that's between them, and the distance that form a right angle, or sometimes we call a H. Okay, it form a H, or sometimes I form an I. Okay, let's see. It form a H. Okay, this is what I mean by H or I. Okay, so this will be the perpendicular distance I'm talking about. Okay, shortest distance between them. So that will be the perpendicular distance that I need. Okay, so the technique I repeat is I will actually copy the direction of the force. I'll place it at the pivot. Then after I get a ruler, I'll just find the shortest distance between them. Shortest distance, normally I just equate it to the alphabet H and I. Okay, so for the students to actually understand it. Okay, then after that, once you have the perpendicular distance, okay, so you'll know that, so sorry. So for this, I will know that if my force is F, the perpendicular distance I'm actually interested in will be D. Denote, so sorry about it. Okay, denote by D. So moments will be F times D. Okay, and this is actually option A. Okay, so take note of how I look at how do I derive perpendicular distance. It's actually quite a standard the way of doing it. It's just that you have to be getting used to it. But one thing to take note, to caution students, is that perpendicular distance, when we talk about perpendicular distance, okay, it may or may not be the pivot. It may or may not be the actual distance. It may or may not be the physical distance of the beam itself. It may be on the beam itself, or it may not be. For example, in this case, okay, the beam is actually here, the pole is here, but the perpendicular distance is actually here. Okay, so the perpendicular distance in this question here we are looking at is not the physical distance on the pole itself. Okay, so take note of the criteria. Okay, perpendicular distance has two conditions. These are the two of them. Okay, so please take note of it. Okay, CG number 8. Okay, basically is I need to find one of the shapes whereby the triangle is can be balanced again, or what we call CG, or what we call the mass is actually distributed evenly. So I would say the answer, if I'm not wrong, is actually this one. Okay, so in the sense that if I have my ruler, I have my pole on this location, okay, the mass on the left hand side would be balanced out by the mass on the right hand side. So what I call center of gravity is actually another name for it called center of mass. Okay, whereby the mass on both sides actually even out or balance out. Now, number 9, number 10, number 10. Okay, number 10, the common question I have, number 9. The common question I have is actually on location 1. Okay, location 1, what we are looking at is if the car is moving, let's say if I shift the car a bit to the left, a bit to the right, okay, the car will be still on this plateau here. Okay, so the center of gravity has not changed at all. When I move left or move right, it has not raised, it has not fallen, it has not become unstable, or nor has it become stable actually. Okay, because there's no position to return to. Okay, so at this point A, because if I move left and right, the CG of the object actually remains the same height. And because of that, I know position A is actually neutral. Okay, for position 2 and position 3, okay, most students actually, or all the students actually know that position 2 is stable, position 3 is unstable. Okay, the only thing is whether or not the students actually recognize position 1 is considered neutral equilibrium. Question 4, nothing much. It's just to take a look at the CG. Okay, for example, if the object is empty object, the CG will be somewhere here. Okay, so likewise, it will be somewhere here for this guy. For the object, okay, for B, the common thing I have is whether I choose B or C, A or B. So how do I derive answer to be B? Is because when the object is originally the CG, if you look at the empty object, okay, the empty object, the CG is here along this line. Okay, so now what happens is when I have water fill up, okay, in this way, I fill up all the way here, you'll find that because it's heavy, the water is heavy, it will actually make the object more stable. So with water here, it actually allows the object to be more stable. Why? Because when water is being poured inside, the CG actually get lowered down. Okay, so lowered down to this position. So because if you look at it, what happened is now is that because of the water, the CG actually get lowered down. Okay, so actually originally the CG was here, maybe it get lowered down to this particular location. Okay, so if you look at B and D, the CG for B and D is the CG get lowered. Okay, so both have the same condition. I will not know who is, maybe we are not sure, or you are not sure who get lowered more. But another factor that will definitely make B stand out is because B has a broader base. B definitely has a broader base as compared to D. Okay, so this guy actually, the option B actually has a broader base. Okay, so even though it could be the case whereby you might assume that both B and D, the CG get lowered maybe to the same degree, but because B has a broader base, confirmed broader base than D, okay, B will actually be much stable. Okay, will be altogether, it will be the most stable among all these four options. Okay. Now, so with this, we come to the end of this section, what I call the MCQ section. Okay, if you are not sure about any of the questions, okay, if you did not catch the MCQ, okay, feel free to pause the video and go back to the particular section. And similarly, I remind you again, if you need, like, maybe a particular question, okay, maybe section B or section C, we just scroll to the necessary timing and just read the video. Just take what, just listen to what you need or what you miss. Okay, do not listen to the whole video because for the sake of listening. Okay, because it's actually quite long. Okay, now for question 1, is a drawing of forces, or what I call vector addition. The whether you use parallelogram method or use tip to tail method, it doesn't matter. Okay, I think all my students actually did quite well for this. So the exact working for parallel or tip to tail method, I will not go through. If you need to, same thing. Okay, the video is in my playlist on chapter 2 or chapter 3, vectors. Okay, vector addition, chapter 3. If you take a look, I actually outlined 2 methods: vector additions, tip to tail, and vector addition parallelogram method. Okay, whichever method you want to be good at, it can be both or it can be one of them. It doesn't matter, because most of the time the question doesn't specify a particular method. It's just any method. Okay, now for part B is, let's say what you need to know is that when you add up all the forces, let's say you have 3 forces here, T, okay, these two, it will actually balance up with W. So what you're looking at for is when you look at resultant force of T, both T's together, 2T, we are looking at the resultant force. It must balance off with the weights. Okay, so what we are looking at here is that the resultant force of these two, okay, which is a part A, the resultant force here, what we are looking at is it must be the same magnitude as your W. Okay, and what we call to balance out, to counteract W, RF, the resultant force must be in opposite direction as compared to W. Okay, that's what I mean by 3-force system. Okay, 3-force system literally is this common property is that 3-force system is like regardless of which 2 force you add, it can be T plus W or T plus T. Okay, the resultant force of the 2 forces, the resultant force must actually satisfy 2 conditions. The magnitude you end up with, it will be the same magnitude with the 3rd force, and it's always opposite direction with the 3rd force. Okay, because all the 3-force system we are looking at O level, okay, the 3-force system are actually more or less balanced. Okay, the object will be balanced under the 3-force system. Okay, and under the 3-force system, whereby it's balanced, you will have 2 properties here, whereby the resultant force of the 2 force is actually of the same magnitude as the 3rd force, and is also the opposite direction as the 3rd force. So that's why I know that if my FR resultant force is 61 Newton here, I will know that this is actually 61 Newton. Okay, exactly the same. Okay, so part C, state 1 differences between mass and weight. Okay, I will not do too much here. Okay, it's always in the textbook. Okay, you refer to it, choose any one. Not usually I just choose the shortest. Okay. Now, if the angle of increase to 60, okay, if the angle increase to 60, the tension T actually, the tension experienced in the force will actually be larger. Okay, if you're not sure, okay, you can actually go and draw it out. Okay, do a fast check of drawing, you'll find that actually the T will actually be higher when the theta actually increases. Okay. Now for question 2, For question 2 is a density question. Okay. Oh yeah, sorry. For 1D, okay, what the question is talking about is like that. So it could be originally is this angle. So this is the angle I'm talking about. So the other one that it could be maybe is that the force, now what happens is the angle is larger. It could be maybe the string is shorter, or maybe it's being put, it's being hang like further apart. Okay, so the theta here actually increases. So it could be this guy is 40 degree times 2 theta. Okay, remember the picture. Theta is one side only. This is 40. Okay, so 40, 40 is 80. Okay, so this is 80 degree. So maybe now this theta here, it could be maybe 120 degree. Okay, so the angle actually increases. Okay, so what will happen? Okay, the tension actually will be increases. Okay, as the angle go wider. Now for question 2, what we are looking at is density question. Same thing, the formula that you need to be sure is density is mass per unit volume. Okay, so I would say it's quite straightforward. You need mass A, you need what you want to find mass A, you definitely need volume A and volume B. You need mass of A, you definitely need volume of A and density of A. So don't mix up the two. Likewise, if I need mass of B, I will need volume of B and density of B. Okay, so nothing major here. Okay, and common thing, density of alloy. Okay, X is always, if I need density of alloy, I will definitely need mass of alloy and volume of alloy. Okay, do not use a shortcut. Do not just simply say, hey, alloy is made of, alloy X is made up of two material A and B. Okay, so what I'm going to do, I'm just going to use density of A plus density of B. Then after that, what I'm going to do, I'm just going to take average divided by 2. That would be my answer here. Okay, do not use this way. Do not use this method. Okay, density is not like, it's not averaging. Okay, you just can't add up all the mass, and after that you just want to like make sure that they just average out. Okay, so take a look at it. Okay, give me a minute first. Okay, so like I mentioned before, remember for density, okay, if I need a density of alloy or what I call composite object, okay, do not just take density 1 plus density 2 plus density 3 then divide by 3. Okay, it doesn't work this way. One alloy or composite object, if I need the composite, okay, or alloy, I need the mass of the alloy, I need the mass of the volume. So you must actually make a direction to it. You must actually find the mass of the alloy first. Then after that, you find the volume of the alloy. Okay, it has to be a separate thing. So if the alloy consists of 3 composite, you literally have to add mass of A, mass of B, mass of C, add them together. Then you have to find the volume of A, volume of B, volume of C, add together. Then after that, you take the ratio between the two of them. Okay, the total mass divided by total volume. Okay, so there is no shortcut to it lah. Okay, for part C, okay, Mike commented the alloy will be lower if it's on moon. Okay, so one hidden message behind this sentence is actually moon. So I actually require, or most of us require students, we don't need the students to know the exact gravitational field strength of on moon, but we definitely need students to understand or to be aware that the gravitational field strength on Earth, okay, as compared to moon, is actually much bigger. Okay, so this is what we call the basic things that the students need to know. Okay, he or she doesn't need to know the exact number, but he definitely need to know that the gravitational field strength of on Earth is 10 Newton per kg, and he or she definitely need to know that the moon gravitational field strength is definitely lower than Earth. That's it. Okay, and likewise, okay, it's also mentioned here. Okay, but even if I don't mention, you also need to know. Okay, and thus the alloy is actually lighter. Okay. Now, when we talk about lighter here, in this context, we are looking at maybe in terms of density. Okay, so lighter here, okay, it could be lighter here. It could be refer to two meaning. It could be referring to the density is lighter. Okay, the density itself is lighter. Density is lighter, or actually it means that it could mean the mass is lighter or mass is smaller. Okay, so either, oh, what happened to my handwriting? Why is it so ugly? Okay, so either way it is not true, because on moon, even though the gravitational field strength is actually lower, okay, gravitational field strength has no impact on density. Okay, this is the symbol for density. Oh, what happened to my pen? It's so ugly now. Okay, density, and it actually has no impact on mass. Why? Because mass is the amount of matter in the object. Okay, amount of matter, okay, in the object. So regardless of the field, whether it's the moon, or regardless of the location, whether it's on moon or on earth, the density, okay, which is independent on the mass, is actually remains the same. Okay, and the mass itself, the amount of matter, it also remains the same regardless of location. So either way, okay, because of the independency of these two factors, okay, the density and mass, my statement to say it is lighter, okay, is actually not valid one. Okay, so you, as in, like, for me, it's like students, you can craft any, depending on which one you want to explain, whether you want to explain lighter with respect to density or lighter with respect to mass. Okay, both is okay, both are accepted. Okay, as long as your concept is good, it's firm. Okay, I don't see why you shouldn't be getting the marks. Now for question 3, okay, is a what I call two pivot system. Okay, now here to take note is, although the object is, there's a uniform rod, so the first clue is uniform. Uniform here, automatic means the CG is in the center. Okay, the CG is at the center. Okay, so automatic is at the center, means CG is at 1 meter mark. Okay, and the CG has a weight of 100 Newton. Okay, and there's two string here. So I'm looking at string A, which is TA, and looking at string B, which is TB. Okay, so the CG will be here. So this will be the CG. Okay, even though the question never state explicitly, I actually know that, okay, this distance is actually 1 meter. From here to here is actually 1 meter. Okay, because CG is uniform. Okay, so these are the clues that's given to the students. There's clue that's given to you, and you have to pick it up. Okay, so likewise now, so once you're ready, okay, and once you're ready, you can actually start to solve the question. Okay, by taking moment about B. Okay, now some of the students highlight to me that you don't understand what the question want, taking moment about B. Okay, here in layman term, it just means that, okay, the pivot is at B. Okay. Okay, so you are talking about taking moment at B. You are talking about the pivot at B, and the other information we are looking at is moments. So I need you to apply moments equation. Okay, apply moments questions. Okay, then after that I need you to apply moments at the pivot B. So now B is my pivot. Okay, so same thing, clockwise, you go in clockwise. So let's look at them first. Okay, first thing first is 100 Newton. 100 Newton with respect to the 1 meter. With respect to the pivot, the perpendicular distance I'm looking at is actually 1 meter. So this is my 100. So I will say that if I'm looking at the force here, which is 100 Newton, the perpendicular distance will be 1 meter. And the moments generated by the 100 Newton is actually anti-clockwise. So this will be anti-clockwise. I will say M100, green color. Okay. Now, B will not have any moments because B cuts through the pivot. So perpendicular distance is 0. So I can actually ignore B. Okay. Then after that, I will actually have TA, tension in string A, which is actually from the pivot all the way to the force TA. This distance is actually 2 meter. Okay, the question say already, 2 meter, and that's my perpendicular distance. And because TA is pointing upwards and is on the left side of the pivot, this moment here will actually be a clockwise moment. I label it as MA. Okay, force is TA, distance is 2 meter. Okay, so these are the two forces. Now, common things that one of the common mistakes that I see in students is the students tend to forget about the 20 kg. Okay, there are 3 forces here we are looking at. One is the 100 Newton, which is the weight of the ruler rods. then followed by tension A, and the lastly is actually the 20 Newton here. Now 20 Newton, remember when we're looking at moments, the formula we are looking at is force times perpendicular distance. It has to be a force. So 20 kg, I will not accept it. You cannot use it. So you must convert it to Newton first. So it will be, let me use another color. Okay, so this 20 kg, I must convert it to 200 Newton. Okay, oh, why so ugly? Okay, 200 Newton. Okay, and similarly, the perpendicular distance is actually measured from the pivot all the way to the force here. Okay, now here take note, given that this is 0.5 meter, okay, away from A, and the whole ruler is 2 meter, I will know that this blue color line is actually 1.5 meter. Okay, so and similarly, blue color line is actually the blue color line, the force is pointing downwards. Okay, which means it will actually generate an anti-clockwise moment here. M200. Okay, so if you look at it, I'm looking at 2 anti-clockwise moment and 1 clockwise moment. So if you look at part A, you look at the principle of conservation, principle of moments. Okay, you will find that for anti-clockwise, there is actually 2 moments. Okay, first one is the 20 kg. Remember, the 20 kg, you must convert to Newton. So you must times the gravitational field strength. So it will be 200 Newton here. Okay, so this will be actually what we call your M200. Followed by your second anti-clockwise moment, which is my M100, which is here. This is my M100. Okay, followed by my MA. Okay, then after that, you let your algebra do your work. Okay, you should be able to arrive at the answer TA, tension in string A to be 200 Newton. Okay, quite easily done. Huh? Now, same thing for tension on B. Okay, tension on B, what you need, there are 2 ways of looking at it. Okay, you can actually do Newton's principle of moments again. Okay, but what you are looking at now is you actually take moment on the other side, which is at A. Okay, so now you take moment at A. So if you are looking at part B, one of the way they are looking at is you actually take moment at A. Okay, you take moment at A, same thing, tension A will disappear, but tension B will be appearing, which is what you need to find. Okay, tension B, and same thing, there are 3 forces we are looking at. One is your 200 Newton, the other one is your 100 Newton. So you will also have 3 forces, and similarly, you will have actually 3 moments. For example, 100 Newton now with respect to pivot A. 100 Newton now, okay, is a clockwise moment. Okay, M100. 200 now, 200 Newton, my 200 Newton here, okay, with respect to A is also anti-clockwise moment, M200. My TB, okay, is a, sorry, what am I saying? Okay, mistake, let me rewind a bit. My M100, my green color one, M100, and my M200, the red color, they are clockwise moment with respect to A. Okay, then for my TB, okay, tension in the string B with respect to pivot A, this guy will be anti-clockwise moment. I will label this as MB. Okay, then after that, same thing, once you have your moment equation, you just do your clockwise to anti-clockwise. Okay, now the only difference now compared to part A is I actually have 2 clockwise moment. Okay, and I only have 1 anti-clockwise moment. So you equate them, okay, in this equation, and you get answer TB to be 100. Now, this is one way of solving using moments. The other way of looking at it is you solve it in terms of Newton's law. Okay, since the object is not moving anything, it's not moving up and down, so it's what we call in equilibrium. You actually got 4 forces that is happening here. 4 forces. For example, there's a TA here, upward force. Oopsie. TA. There's an upward force, TB. And there is actually 2 downward force, which is first is the 200 Newton. Second is the 100 Newton. So you can actually do a simple F net, or what you call Newton's second law, whereby you look at the net force on the system. Okay, so you actually have two upward forces and two downward forces. Okay, two upward forces, okay, and two downward forces. Okay, so you will have two downward forces, which is here. Okay, then after that, you equate them to MA. Okay, and of course, in this case, students, you may wonder, where is the acceleration? Okay, and remember the question says is in support. Okay, so it means the question says in support. Okay, in support means it's actually in balancing, it's actually in equilibrium, aka it is not moving at all. So my acceleration is actually 0 meter per second squared. Okay, same thing, if you do Newton's law, the equation will look like this. Okay, this is the equation for Newton's second law. If you use F net equal to ma, okay, you will have two forces here. Okay, two upwards and two downwards. You equate them together, you solve for the unknown TV, and you get it as 100 Newton. Same answer. Okay, so two different approach, but actually the same answer. Okay, now which of the string will snap first? Okay, the string obvious one is string A. Now, how do we explain it? Okay, now the easiest way to explain it, if you look at it in terms of moments. Okay, now what happened here is based on the question is the object, the 200 Newton is the one that's being shifted. So 200 Newton, okay, it could be hanging here at the beginning. Then after that, I shift it to this side. Okay, so I shift it to this side. So what we are looking at is as when I shift to A, the tension in string A, how does it change? Okay, this is most straightforward. As in, it's most obvious when I take the moments about pivot B. Okay, when I take the moment about pivot B, you'll find that my TA, okay, if I take moment at B, you'll find that my TA perpendicular distance remain the same. Okay, so my TA anti-clockwise moment MA, sorry, the clockwise moment MA actually remains the same. The distance actually remains the same. The perpendicular distance, the perpendicular distance for TA moment A actually remains the same. Okay, but what happened now is this. My perpendicular distance remains the same, but it doesn't mean that my clockwise moment MA remains the same. It doesn't mean it. But I do know one thing is that I need my MA because my clockwise moment must balance with anti-clockwise moment. So what happened to the anti-clockwise moment first? Okay, now when I shift the 200 Newton from position 1 to position 2, move it further away, move it nearer towards A, you'll find that my perpendicular distance, okay, actually increases. Okay, so in this case, right, you will find that my perpendicular distance, my d perpendicular distance of 200 Newton, as I shift the 200 Newton nearer to A, my perpendicular distance actually increases. Okay, and remember the perpendicular distance we are referring to is referring from where? We are referring from the pivot B all the way to 200 Newton. Okay, oh, cannot see. Okay, so you'll find that as my 200 Newton shift towards A, okay, my anti-clockwise moment actually increases. Okay, as I move my 200 Newton move further away or move towards A, my perpendicular distance of the 200 Newton actually increases. And because of that, my moments, okay, to be exact, my anti-clockwise moment of the 200 Newton, okay, actually increases. Okay, take note here, the moment for the anti-clockwise Newton, okay, the anti-clockwise Newton actually increases, not because the force increases. The force still remains at 200 Newton, but it increases because the perpendicular distance actually increases. Okay, then because the perpendicular distance, the anti-clockwise increases. Okay, the clockwise moment increases. My anti-clockwise must remain the same. Okay, my clockwise moment, okay, must increase. Why? To remain equilibrium. Because remember, the two string of the rod or the rods has to be balanced. So if my clockwise moment increases, okay, my anti-clockwise moment increases. This is my anti-clockwise moment. As my anti-clockwise moment increases, my clockwise moment okay, my clockwise moment okay must also increase. Okay, why? To balance, because the rod is in equilibrium. So my anti-clockwise moment has to be equal to anti-clockwise moment. The two side moments must be increased or must be balanced. So if my anti-clockwise moment increase, my clockwise moment must increase. And my clockwise moment, how do I increase? My clockwise moment, my perpendicular distance is the same one. It's always the same. So how do I increase my clockwise moment? Only one way only. Okay, my force A must increase. Okay, and the bad thing about this is when my force A increases, okay, force A will be of certain it will snap eventually, because the question say the string exit 220, it will snap one. So in this case is as the box move nearer to A, okay, the force in A has to increase because the clockwise moment has to increase to maintain equilibrium, and because to maintain equilibrium, force A has to increase, force A will snap, or the force in string A eventually will snap. Okay, so this is one of the problems that we are looking at. Now, for section C, I would say it's a straightforward question. Actually, section C, the only problem or the only difficulty I see in students' paper is that the students actually can't relate section A with section B. They will just ignore section A, the information in section A when they are at section B. Or some of them, they actually ignore the clues that is given in section A. And as a result, it affects the whole entire question. For example, this, okay? During the landing, okay, there is a two-stage landing process. Okay, so meaning stage 1 and stage 2, they are related ones. Stage 1 and behind, where's stage 2? Stage 2, they are related one. And in fact, after stage 1, it becomes stage 2. So these two stages are related. So certain information are actually roll over from stage 1 to stage 2. Okay, so student, you have to be careful. Then after that, there is given in the question, there's it lasts for 15 minutes for stage 1. The forces, outward forces is 24 kilonewton, aka 24,000 Newton, kilo. Oopsie. Oh, my handwriting is so ugly. Okay. Oh, give me a minute. Okay, 24,000 Newton. Okay, and the object, okay, and definitely the object has to have mass. Okay, so there's definitely have weight. And after that, he moved vertically downwards with a constant speed of 600 meter per second. Same thing, important thing is to steady speed, or sometimes we known as constant speed. Okay, this information is very important because this information actually tells us one thing. Constant speed means what? Acceleration equal to 0 meter per second square, aka means the common thing, F net equal to 0. Okay, so this is the important thing that you have to be careful. Okay, these are the clues that's given in the question. Okay, so that you must be aware of, okay, before you start anything. So you will need all this information later on. Drawing the forces, okay, it's straightforward. Okay, draw the weight. Okay, then followed by the upthrust. Okay, the only thing you take note is that of the location. Okay, the forces, both forces must be drawn from CG, or what I call the center of the rocket here. Okay, the location does matter. Don't just draw anyhow, draw an upward force on the left of the rocket or directly above the rocket, all these things. Okay, the location is important. Okay, it's always from the CG. Yeah. Mass of the space shuttle straight away. This is the booby trap. Now, this is what I mean by you have to be aware of the clue. Okay, the moment I say steady speed here, I'm actually telling you F net is acceleration is 0, F net is 0 already. So this piece of information actually is rolled over, okay, to part 2. Okay, F net equal to MA. F net equal to MA, there are two forces here. Okay, A is not unknown that you need to use the formula. Very commonly, I see students using V equal to U minus delta T. But there isn't a need because the question already tell you it is a constant velocity already. The question already say it is a constant velocity. Okay, he already say it's a constant velocity. So all you need to do at constant velocity, we mean acceleration is 0 straight away. There's no need to find the acceleration. It's actually 0 already. So if you submit 0, acceleration is 0, F net equals 0, you will find that you will arrive at this small expression, this equation. Your force will be equal to the upthrust, which is 24,000 Newton. And same thing, gravity based on the question is 1.6 Newton per kg. You'll know that the mass is 15,000 kg. Okay, so here take note of the question here. Okay, take note of the information that I'm giving you, the constant speed, what is the upthrust to 24,000, all these things. So you have to be careful of information given to you. Part 2, okay. Part 2 now, the question says the upthrust increased to 26,000 Newton. Okay, upthrust increased to 26,000 Newton. Okay. Then after that, he reaches the speed at 400 meters per second. Okay, now take note, the trap or the clue that's given to you is that both are linked. Part A and part B are linked. So you'll find that at part A, the speed is 600 meters per second. Okay, now at part B, stage 2, the speed I'm looking at is actually wrong arrow. The speed I'm looking at is actually 400 meters per second. So from 600 to 400, there is actually an initial speed and final speed. This is my final speed now. Okay, and this is actually my initial speed. Okay, my initial speed. Okay, so there's an initial, there's a final one. Okay, and likewise, okay, same thing, calculate the acceleration. Okay, now so far the acceleration we are looking at. Okay, now so far the acceleration that we're looking at, there is a 600 to 400. Okay, your original speed was 600 meters per second. Now you are having a 400 meters per second. So if you put in these two numbers, you'll find that the information or the clues that is hidden behind this number is actually what we call acceleration is actually negative because the object actually decreases speed. So he is actually experiencing a deceleration or retardation, which means if I'm looking for acceleration, I expect this number to be a negative number. Okay, and true enough, okay, the weight remains 24,000. Upthrust is 26,000. Remember, this is 26,000 now. Do not write 24,000 again. Mass is 15,000. Fine, and you'll find that the answer is negative 0.133, which actually further support the fact that okay, it has actually reduced its speed. Then after that, okay, the next clue that I given to you, because I know I'm supposed to find acceleration, I'm supposed to find time using the acceleration formula. And because based on part A, remember the 600 meters per second, okay, this information, okay, 600 meters per second, okay, the initial speed is actually 600 meters per second. The final speed is actually 400 meters per second, given in the question already. The common fault that I see in students that he or she can't answer these few particular questions is because he can't make sense of, or he can't relate part A and part B, stage 1 and stage 2. He sees stage 1 and stage 2 as separate stages, separate question. And because of that, he or she can't actually answer the question. Okay, so one advice I have for students is actually read the question carefully. Okay, don't assume, don't anticipate the questions. Okay, read the questions to sieve out the clues that is given by the marker. Okay, in reality, okay, the answer will be different. Okay, how is it different? Okay, one obvious one is when in reality we are talking about fuel. As I produce the upthrust, which is from the engine, 24,000 Newton, 26,000 Newton, when I produce that upthrust, okay, in order for me to produce the upthrust, my engine has to be running. And because my engine is running, okay, the fuel in the spacecraft will actually be decreasing. And I'm burning my fuel, okay, to produce the upthrust, to have a constant upthrust so that I can actually reduce or to slow down my rocket or my shuttle. And because the fuel is reducing, the mass of the card is reducing. And because the mass is reducing now and actually getting lighter, okay, I'm getting lighter here. And because of that, my deceleration, my retardation that I experiencing actually will become bigger. Okay, it'll be easier to slow down my object. It will be easier to slow down me. Okay, because the shuttle, okay, is getting lighter and lighter. So with the same upthrust, I'm able to slow down the shuttle even more. So this is what I mean by, because I am able to slow down my shuttle even more, in real life, I actually will take a shorter time to actually reduce or to slow down my shuttle. Okay, according to the landing process, okay, 1 and 2. Then after that, the part C question is why I don't use parachute for landing process. Common, you will say it's a common thing that we use for parachuting. Parachuting here on Earth, we use parachuting. The moment you want to parachute, I want to increase my air resistance. Okay, and what I want to do is I want to reduce my terminal velocity. I want to slow down my terminal velocity. Okay, so that I will not crash down on the earth straight away. But for me to actually for me to use parachute, the ultimate objective I'm looking at is actually reduce the speed, which is currently what the shuttle is looking for. The landing process, stage 1 and stage 2. I want to reduce my speed. But for parachute to be effective, the main important thing that I must have is I must have air resistance. I must have air first. So as long as I have a big parachute, I have air, I have abundance of air, I will definitely have air resistance. And with that, it actually allows me to reduce my free falling, allow me to reduce my terminal velocity, okay, quite drastically. But the main function I'm looking at is I must have air resistance. And on Moon, there's hardly any atmosphere. Okay, there hardly any big amount of air. Okay, maybe some minute gases up there, but definitely not enough. Okay, if you compare to Earth. So there's little or no air resistance. And because of that, I have no air resistance. There's no way I can actually reduce my landing speed. Okay, and that's one of the reasons why in the landing process 1 and 2, I do not use parachute because it's actually ineffective, no matter how big my parachute is. Okay, because there isn't enough air or air resistance, okay, in the atmosphere of the Moon. Okay, with this, okay, we come to the end of the paper here. I hope I have actually helped to reduces your doubt. Okay, so if you have any questions, I do hope that I've answered some of them, or if not most of them. Okay, but in other words, okay, in just in case if you have any other questions that you want me to address or I have not addressed, okay, feel free to leave your comments at the comment bar below. Okay, I will be uploading one more paper, the Sec 4 papers. Okay, if you're interested, if it's relevant to you and you want to get updated to that particular paper, okay, remember to like my video, my channel. Okay, and click the bell button so that you get notifications whenever I upload new things and new materials that is of use to you. Okay, if not, okay, it's very late now. It's like almost midnight already. Okay, have a good rest. Okay, to everyone, you and me. Okay, and see you soon. Bye bye.